Well, the spacecraft went behind Mars when it obviously cannot communicate with Earth, but when it came back, there wasn't any contact, no signal, and NASA is trying to figure out.
Yeah, and MAVEN theoretically would have taken photos of 3I Atlas, is that correct?
Yes, it did already, and we saw some data from it.
So there you go, and NASA now claims, whoops, well, all of a sudden MAVEN is gone. We don't have contact with MAVEN, meaning we can't release those photos publicly. Okay.
NASA has a rule they rarely talk about. When something in space starts moving in ways it shouldn't, when the math stops adding up and predictions fail, they don't announce it on the evening news. They activate protocols quietly. On November 27, 2025, they did exactly that for 3I/Atlas, an interstellar comet they insist poses no threat to Earth. And that raises a question that should bother you. Why would a harmless comet trigger a 2-month planetary defense campaign involving hundreds of telescopes and coordination through the United Nations? Stay with me, because by the time we're done, you'll see why this isn't just about studying a comet. It's about watching something that might turn. As 3I/Atlas plunges further into our solar system, every new observation brings us closer to understanding what we're really looking at. Subscribe and follow along, because the data is coming fast and every frame matters. Now, let's dim the lights and dive into this cosmic mystery. NASA told the public there was nothing to worry about. On July 20th, 2025, they issued a press release announcing the discovery of 3I/Atlas, an interstellar comet passing through our solar system. The language was technical, measured, almost boring. No threat to Earth, standard observation protocols, just another visitor from beyond, like Oumuamua in 2017, or 2I/Borisov in 2019, business as usual. Except it wasn't. Behind the scenes, NASA quietly activated the International Asteroid Warning Network, not just turning it on, but launching Campaign 8, a 2-month continuous observation blitz involving hundreds of telescopes across 6 continents, coordinated through the United Nations Office for Outer Space Affairs. The campaign started on November 27, 2025, and will run through January 27, 2026. 62 days of synchronized observation for an object that officially poses no danger. To put this in perspective, the International Asteroid Warning Network exists only to track potential impact threats. It's not a science club. It's a planetary defense mechanism born from decades of near misses and Hollywood disasters, finally convincing governments to watch the rocks flying past Earth. When IAWN activates a campaign like this, it means something triggered their threat assessment protocols. Orbital calculations produced a probability curve that someone somewhere didn't like. So why do this for a comet that, according to every official statement, has 0 chance of hitting us? Here's the official story. 3I/Atlas is an interstellar visitor. It was first spotted by the Atlas Survey Telescope in Hawaii on July 1, 2025. Observations showed a hyperbolic trajectory, a hallmark of an object not bound to our sun. It would swing past, gain some gravitational acceleration, and slingshot back out into interstellar space. Textbook interstellar flyby. Nothing unusual, nothing threatening. But then something strange happened. In late October, after 3I/Atlas passed behind the sun from Earth's perspective, astronomers picked it up on the other side, and its orbit didn't match predictions. Not by a little, but enough that multiple recalculations were required. Comets drift. That's normal. They're icy, they heat up near the sun, ice sublimates, jets of vapor shoot out, and these jets act like tiny rocket engines, nudging the comet off course. Astronomers account for this non-gravitational acceleration. It's expected. It's boring. What isn't boring is when the drift doesn't match the outgassing pattern. What isn't boring is when the acceleration vector points in a direction that makes no physical sense. And what really isn't boring is when this new trajectory threads precisely toward Jupiter's gravitational sphere, a path natural physics should make essentially impossible. Suddenly, on November 27th, Campaign 8 begins. Hundreds of observatories worldwide pivot to track 3I/Atlas. Amateur astronomers receive coordinated observation requests. University research telescopes are bumped from their scheduled programs. Even military tracking stations, usually focused on missile launches or space debris, start contributing. All for an object that supposedly poses no threat. You don't mobilize an international planetary defense network for a routine scientific curiosity. You don't coordinate this level of global resources unless you're looking for something specific. And you definitely don't do it quietly, keeping the campaign details out of the media, unless you're concerned about what you might find. Compare this to Oumuamua, the first confirmed interstellar object in 2017. Cigar-shaped, tumbling, showing unexplained acceleration. Some suggested it could even be artificial, but NASA didn't activate a planetary defense protocol. They observed, published, debated. They let it leave. No emergency mobilization. 2I/Borisov in 2019 was even more ordinary. A typical interstellar comet. Nice pictures, a few papers, and everyone moved on. So why does 3I/Atlas get the full planetary defense treatment? Leaked internal memos from IAWN partner institutions shed some light. Documents not meant for public eyes. They reference trajectory anomalies, multiple course corrections, and something called CCM2, Course Correction Maneuver 2. The word maneuver is chilling. Maneuvers aren't natural. Spacecraft maneuver. Satellites maneuver. And now, apparently, so does this comet. Rocks in space, even unusual interstellar rocks, don't maneuver. They follow predictable paths, dictated by gravity and momentum. They don't correct their course. The timeline tells a story that NASA's press releases never do. July 2025, discovery and initial excitement. August-September, routine observation. Everything looks normal. October, 3I/Atlas passes behind the sun. Temporary loss of tracking. Late October, object reappears. Trajectory is wrong. November, frantic recalculations. New predictions show a precise approach toward Jupiter. November 27th, IAWN Campaign 8 activated. And here you are, reading this, wondering why you're only hearing about it now. Here's what they're not telling you. Standard planetary defense drills. Those IAWN conducts to test protocols are public. They use fictional scenarios or objects that are decades away from any potential impact. Training exercises. Zero real-world stakes. Campaign 8 is not a drill. It's real-time data from a real object, and it's happening quietly, while NASA keeps reassuring the public that everything is fine. If 3I/Atlas is just a comet, a natural visitor passing through, why the secrecy? Why the mobilization? Why does the largest coordinated observation campaign in IAWN's history coincide with an object showing unexplained trajectory changes? We've been told there's no threat, but someone activated planetary defense anyway. That gap between what we're told and what's happening, that's where the real story lives. That's the question that should keep you up at night. What do they know that they're not saying? Consider this. In March 2025, 4 months before the official discovery, an internal document appeared on the European Space Agency's network. It wasn't public, just a logistics brief for telescope time allocation, the kind of boring admin paperwork that keeps space observation running, except for one line buried in a table. Anticipated interstellar inbound candidates, early anomaly projection, high priority. Let me repeat that. 4 months before anyone knew 3I/Atlas existed, ESA was allocating resources to observe anticipated interstellar objects showing anomalies. Not potential objects, not hypothetical objects, anticipated objects. As if they already knew something was coming. The document leaked in early November. Around the same time, the trajectory anomalies became impossible to ignore. Posted anonymously on a forum frequented by amateur astronomers, the PDF's metadata showed creation in late March 2025. Authentication is tricky, but independent analysts confirmed that the formatting, language, and internal reference codes match legitimate ESA planning documents from that period. If it's a fake, it's an extraordinarily good one, crafted by someone with inside knowledge of ESA's bureaucratic systems. And it's not the only hint. Similar references appear in budget requests from partner institutions in the IAWN network. The University of Arizona, which operates several survey telescopes, submitted a funding request in February 2025 for enhanced monitoring of trans-Neptunian trajectories and interstellar candidate surveillance. Funding was approved unusually quickly, released by April, months before the July discovery announcement. Then, there's what doesn't leak, the things we can only infer. The U.S. Space Force quietly upgraded several infrared tracking satellites in late 2024. These satellites normally track rocket launches from Earth, sensing heat from exhaust. In November 2024, at least 3 were reoriented outward, scanning deep space. Why? Military notes speculated debris tracking or classified satellite observation. Nobody suggested looking for interstellar objects. But infrared telescopes excel at spotting cold, distant objects, better than visible light telescopes, because they detect faint thermal emissions, not reflected sunlight. If you wanted to spot something coming from the outer solar system, far enough away that it hasn't brightened yet, you'd use infrared and wide-field sensors designed for rapid threat detection. That's exactly what these satellites were doing. By January 2025, 6 months before the official discovery, someone with access to these military sensors was watching a specific region of the sky. Connecting the dots requires speculation, but the picture is striking. If 3I/Atlas was detected early, if classified sensors spotted it before civilian telescopes, it explains the ESA planning documents, the University of Arizona's early funding, and the prearranged response framework. It explains why intensive observation could begin immediately after the July announcement. But why keep it classified? One explanation: operational security. If the Space Force has infrared satellites capable of detecting small interstellar objects millions of miles away, revealing that would expose sensor capabilities, coverage, and protocols. You sit on the information, quietly prepare, and let civilian astronomers discover the object later. Another explanation: risk assessment. Maybe the initial trajectory looked potentially threatening. Early calculations could have produced concerning impact probability curves, enough to warrant quiet preparation but not public alarm. Or the unsettling possibility: early observations revealed something unnatural. Maybe the infrared signature didn't match a normal comet. Maybe the trajectory was too precise. Maybe there were signs of maneuverability from the start, indicators that this wasn't just a comet, but something requiring planetary defense monitoring. Pre-discovery surveillance implies that when NASA held that July press conference, showing images from the Atlas telescope and announcing the interstellar visitor, they already knew more than they were saying. The public discovery was theater, a controlled release, while the real analysis was happening behind classified doors. This isn't unprecedented. During the Cold War, military sensors designed to detect nuclear explosions, seismographs, satellites, acoustic arrays were also excellent at spotting meteors and space debris. Sometimes, these sensors detected incoming asteroids hours before civilian observatories. What gets shared and what stays classified depends on operational priorities. In that context, the timing of IAWN Campaign 8 makes sense. November 27th wasn't random. That's when the trajectory anomalies became undeniable. When the post-perihelion drift became evident across multiple independent observations, it could no longer be kept quiet. That's when the pre-planned response had to activate. Months of preparation finally went live, and we witnessed a carefully choreographed release of information. Official discovery, July 2025. Routine observations, summer into early fall. Then, just as the object behaved unexpectedly, a massive observation campaign, already prepared, was deployed instantly. That level of readiness doesn't happen by accident. It happens because someone knew long before the public was told that this object was coming, and that it might warrant serious attention. Here's the ghost haunting this story. Somewhere in classified databases, there are pre-July observations of 3I/Atlas. Infrared images, trajectory calculations, threat assessments, all compiled by analysts quietly tracking the object while the rest of the world remained unaware. Those early observations could explain why, when unexplained acceleration appeared months later, a response plan was already in place. Because maybe the object had been exhibiting these anomalies all along. Orbits are supposed to be predictable. That's not an opinion, it's mathematics. Johannes Kepler figured this out in 1609. Objects in space follow ellipses, parabolas, or hyperbolas depending on their energy and the gravitational wells they traverse. Measure an object's position and velocity at one moment, plug the numbers into equations tested over centuries, and its trajectory unfolds with mechanical precision. Adjustments can occur, small corrections for outgassing if it's a comet, but by and large, the math works. This is how we send probes to Mars, orbit Saturn, and land robots on distant worlds. Except 3I/Atlas isn't following the math. After swinging around the sun and re-emerging in late October, it wasn't where it should have been. Not even close. The deviation was so large that some astronomers initially suspected they were observing a completely different object. We're talking positional errors measured in millions of kilometers and velocity changes that standard comet models cannot explain. When comets approach the sun, ice on their surfaces sublimates directly into gas. Jets of material erupt into space, sometimes forming visible tails, sometimes subtle enough to detect only through orbital calculation. Astronomers have decades of experience modeling this, predicting positions, outgassing effects, rotation influences, and trajectories. Their models are reliable. They don't work for 3I/Atlas. The observed acceleration vector, its direction and magnitude, doesn't align with the comet's sun-facing jets or rotation. The force pushing the object is far greater than what the observed brightening could generate. Most troubling, the acceleration appears precisely calculated, nudging the object toward a very specific destination, Jupiter's gravitational sphere of influence. After perihelion, the comet should have been on a steep trajectory out of the solar system. A fast, clean exit, just another interstellar visitor passing through. Instead, its post-perihelion path is unusual, flatter, more aligned with the plane of the solar system, directing the object unusually close to Jupiter's orbit. Not close enough to collide, but close enough to enter the planet's Hill radius, the region where Jupiter's gravity dominates over the Sun's. Within the Hill radius, complex gravitational dynamics reign. Small changes in angle or speed can dramatically alter an object's path. Temporary capture, orbital deflection, or a high-speed slingshot. The odds of a random interstellar object threading the solar system in such a way, aiming nearly perfectly into Jupiter's Hill radius, are astronomically small. Space is vast. The solar system is mostly empty, and yet here it is. Even Jupiter, the largest planet in our solar system, is a tiny target when you're incoming from interstellar space at kilometers per second. For 3I/Atlas to have nudged its post-perihelion trajectory so precisely to set up this approach, we're faced with two possibilities. Either we're witnessing a coincidence of staggering improbability, or something deliberately altered its course. Internal documents label this adjustment CCM2, Course Correction Maneuver 2. Maneuver 2 implies there was a Maneuver 1, an earlier trajectory adjustment that wasn't publicly acknowledged. The terminology is revealing. Maneuver is engineering language, what mission controllers say when they fire thrusters on a spacecraft. It is not how you describe random outgassing from a comet. Avi Loeb, the Harvard astronomer who sparked debate over Oumuamua's possible artificial origin, has been outspoken about 3I/Atlas. He notes that if the trajectory adjustment is deliberate, the required delta, v, the change in velocity to shift in orbit, is relatively modest. For a spacecraft with advanced propulsion, threading a trajectory toward Jupiter's Hill radius would be a logical move. Gravitational analysis of the solar system's largest planet, optimal observational positioning, or even temporary capture into a stable monitoring orbit. A brief burn at exactly the right moment could achieve all this without continuous thrust. The counter-argument is that this is natural outgassing. The cycle's natural. Comets are irregular, rotate unpredictably, and can emit jets asymmetrically. Perhaps, by chance, 3I/Atlas's jets fired at exactly the right moment to line up with Jupiter. Maybe we're witnessing an extraordinarily rare alignment. But that explanation doesn't hold up. To generate the observed trajectory change purely from outgassing, 3I/Atlas would need to expel massive amounts of material. That should be visible, a bright, obvious coma, a long tail, a trail of gas and dust stretching through space. Instead, observations show minimal outgassing activity. The object is remarkably quiet for something supposedly propelling itself off course. Now, researchers are scanning for a potential second burn, a follow-up adjustment as it approaches Jupiter. If 3I/Atlas is under active control, if something or someone is steering it, additional course corrections could occur, and Campaign 8 of the International Asteroid Warning Network is designed to catch them in real time. Hundreds of telescopes across 6 continents are monitoring simultaneously. Any sudden change in speed or direction will be immediately recorded, triangulated from multiple angles, and confirmed beyond doubt. This is unprecedented. Never before has an interstellar object displayed this combination of trajectory precision and mechanical quietness. Never before have we had the observational infrastructure to track, minute by minute, whether an incoming object is obeying natural physics or executing planned maneuvers. This is happening now, in real time. Over the next 2 months, we'll see whether 3I/Atlas continues its current path toward Jupiter or surprises us again with another unexplained adjustment. If this is a natural comet, its motion shouldn't exist. If it's a random rock from interstellar space, this level of precision is impossible. Yet, the motion exists. The precision is real, which leaves 2 uncomfortable possibilities. Our understanding of cometary physics is deeply flawed, or we are watching something that knows exactly where it's going and how to get there. Neither is reassuring. Both demand constant vigilance. If this object can steer once, it could steer again. And next time, it may not aim for Jupiter. Imagine a planet as a king on its throne and something calculating the perfect approach. The Sun is the emperor of the solar system, ruling with gravity that keeps every planet in line. But each planet is a king in its own right, with a territory where its word is law. In gravitational terms, that territory is called the Hill radius, the region where a planet's gravity is strong enough to capture moons, rings, or passing objects, despite the Sun's overarching influence. It's a sphere of sovereignty in the hierarchy of the solar system. Jupiter's Hill radius is immense, befitting the king of planets. It stretches roughly 51 million kilometers from the planet's center, about a third of an astronomical unit, and more than 100 times the distance from Earth to the Moon. Within this sphere, Jupiter's gravity dominates. Anything that enters is at its mercy. Outside, the Sun regains control, and Jupiter is just another gravitational influence among many. 3I/Atlas is on a trajectory that will take it deep into Jupiter's Hill radius, not skimming the edges, not just passing by safely, but penetrating into the zone where Jupiter's gravity will be the dominant force acting on it. Current projections show it coming within 20 to 30 million kilometers of the planet, well inside the Hill boundary. That's threading a cosmic needle for an object arriving from interstellar space. And here's why that matters. The Hill radius isn't just a mathematical curiosity. It's the line between passing through and potentially staying. Objects that enter this zone can, under the right conditions, be captured into orbit, temporarily or even permanently. That's how planets acquire new moons. Some of Jupiter's outer moons are believed to be captured asteroids or cometary nuclei, snagged by the planet's gravity after wandering too close. But for 3I/Atlas, approaching the Hill radius from interstellar space with such precision is extraordinary, like throwing a dart blindfolded across a football field and hitting the bullseye. Physics allows it, but chance makes it astronomically unlikely. And if something achieves that kind of precision, well, it raises questions. The trajectory of 3I/Atlas after its unexplained post-perihelion acceleration lines up almost perfectly for a close approach to Jupiter. The margin of error is measured in thousands of kilometers, tiny compared to the vast distances involved. Multiple independent calculations from observatories around the world, all converge on the same conclusion. This object is heading straight into Jupiter's gravitational domain with a precision that looks intentional rather than accidental. Analysts are quietly considering a few scenarios. The first, temporary capture. If 3I/Atlas enters Jupiter's Hill radius with the right velocity and angle, Jupiter's gravity could slow it enough to trap it in a highly elliptical orbit. This orbit wouldn't last forever. Perturbations from the Sun and Jupiter's other moons would eventually eject it or send it crashing into the planet. But in the meantime, for months or even years, 3I/Atlas could become a temporary satellite of the largest planet in the solar system. And strategically speaking, that orbit is prime real estate. Jupiter sits at the boundary between the inner rocky planets and the outer ice giants. From a stable orbit around the giant, you would have a vantage point over nearly the entire solar system. From a vantage point near Jupiter, you could observe Earth from a distance, track movement through the asteroid belt, or monitor activity around the gas giants. If you were an intelligence, natural or artificial, interested in surveying the solar system without getting too close to the noisy inner planets, parking yourself in Jupiter orbit would be a masterstroke. Scenario 1. Temporary capture. 3I/Atlas could enter Jupiter's Hill radius and be slowed enough by the planet's gravity to become a temporary satellite. Its orbit wouldn't last forever. Gravitational perturbations from the Sun and Jupiter's moons would eventually eject it or send it crashing into the planet. But for months or years, it would have the perfect vantage point. From there, it could observe the solar system while keeping a safe distance from the inner planets. Scenario 2. Gravitational slingshot. Instead of being captured, the object could use Jupiter's gravity to alter its trajectory and speed, just as we've done with spacecraft like Voyager. A close flyby could send 3I/Atlas deeper into the solar system, back out toward interstellar space on a new trajectory, or even toward another planet entirely. The catch: the outcome depends on exact approach parameters. A tiny difference in distance or velocity could produce radically different results. Natural objects have no control over this. They take what gravity gives. A guided object, however, could thread that needle with precision. Scenario 3. Deliberate positioning. Perhaps the goal isn't orbit or escape, but simply entering the Hill radius to exploit its chaotic gravitational environment. Inside this zone, tiny unobserved forces can drastically alter an object's path. A subtle propulsion burn, impossible to detect from Earth, could redirect the object and make future trajectory predictions nearly impossible. This is why the IAWN Campaign 8 exists, not because 3I/Atlas threatens Earth, but because if it can steer itself, its potential destinations are limitless. Traditional planetary defense relies on predictability. We track asteroids for weeks, calculate orbits, and project decades into the future. Asteroids obey gravity. Their paths are slaves to physics. 3I/Atlas doesn't. Its trajectory has already defied expectations. Infrared observations add another layer of concern. Active comets emit thermal radiation as ice sublimates, but 3I/Atlas is cold, too quiet, for the level of trajectory perturbations observed. It's moving without the expected heat signature, like watching an engine drive a car silently. Some researchers speculate about low-thrust propulsion, like an ion drive, capable of altering trajectories quietly and efficiently. The object's anti-tail behavior further complicates modeling. Occasionally, it shows material extending in unexpected directions, not away from the Sun as a normal comet would. Taken together, the brightness offsets, chaotic rotation, hints of structure, minimal thermal emission, and anti-tail activity, 3I/Atlas doesn't fit any known comet profile, once with its post-perihelion acceleration and again with its precise approach toward Jupiter. Each new calculation forces analysts to start over. It behaves more like a controlled object than a natural one. The object's physical behavior deepens the mystery. Comets usually have a bright nucleus, with reflected sunlight coinciding with the center of mass. But amateur astronomers stacking images over multiple nights have observed a brightness offset, the brightest point shifting relative to the object's structure. This suggests either an unusually complex rotation or an extended structure with multiple reflecting components. Images from the Mars Reconnaissance Orbiter, though not designed for interstellar imaging, revealed hints of elongation and distinct bright regions, raising questions about whether 3I/Atlas is a single nucleus or a more complex structure. Its light curve is chaotic, irregular, and unpredictable, suggesting multi-axis tumbling or other rotational anomalies.